Working in a construction environment in and around a healthcare facility for the first time can be a daunting and even an overwhelming experience. Our goal with this video series is to relieve some of that unwanted stress. There are many different trades that work in these healthcare environments, and electrical equipment can be dangerous to any of them. Whether it is new construction of a large hospital or an upgrade to a university medical center or even a critical access hospital, electrical hazards must be considered, as well as ensuring power is not lost for even a very short duration.
In working in a hospital, the work that you do, you got to realize it affects a lot of people. There are people on ventilators, there are people on life safety. So every time you're around something, you have to keep that in the back of your mind. Every day at the beginning of the day, you got to realize that, and every day at the end of the day, you have to realize that. People's lives are dependent upon what you do.
Today, an outage of even a fraction of a second can compromise patient care and clinical networks. All healthcare facilities demand continuous power. In addition, power quality fluctuations can damage sensitive equipment or jeopardize research data in milliseconds.
Another area in a healthcare environment that we often overlook or not consider because we're so focused on the operating table, unfortunately. Research. Think about, we're in a world of trying to prevent, trying to come up with preventions or medications we can take to either reduce the likelihood of you passing away from cancer or viruses. If I have a lab full of research that I need to do studies and I need to see cultures over 6 months and I lose power and I lose that, I've lost 6 months. I could lose years of my research data that will never be replaced. You can't replace that. So it's critical that we keep power going to these other areas in a healthcare environment for those reasons.
When compounded, these challenges establish the need to ensure infrastructure is not only up to date and code compliant, but also ready for unforeseen circumstances. As a contractor working in this industry, you may have the opportunity to work on brand new high-tech healthcare facilities that are designed with all of these considerations in mind. But more than likely, you will also work in many hospitals that were built after World War II and have much older infrastructure and electrical equipment. The challenge to you is to understand what codes and standards need to be considered in each situation. These videos will help you understand some of these considerations. Because of the aging infrastructure in many older facilities, healthcare organizations need to keep a close eye on the condition of their electrical equipment and systems. As a contractor, you may work on some very old equipment in these hospitals, and it may be up to you to recommend changes to make their system more safe and reliable.
Basically, on the whole in the hospital, it's just that from my end that I've worked on any new construction, they are updating to the equipment to the latest technology, but they are not there yet. They're updating their generators, transfer switches, but a lot of their substation work, their old Westinghouse gear, transfer switches, things down, tie breakers, those such things, they usually don't fool with them too much unless they absolutely positively have to.
Just like any organization, hospitals operate on a budget and yet need to be competitive to generate revenue. In an idealistic sense, you might assume that hospitals would have unlimited funds to upgrade to the latest equipment or electrical infrastructure. This is not the case, and in fact, funding for these upgrades often competes with other operational commitments.
You might think that hospitals are designed to have the latest and greatest equipment at all times, but that just simply isn't the case. The economics of it just aren't possible. Every year somebody comes out with something that is a safer system. The technology today is amazing, but having that technology installed is also very, very expensive. So while many hospitals, if they do have regular big upgrades, do upgrade to the safest systems that they possibly can, in many situations, the system before it gets upgraded could be 20 to 30 years old. So if it's 2020, the system you're working on is likely from the 90s. It's not unusual at all to have that situation.
Retrofit and reconditioning options for electrical equipment allow healthcare facilities to lower their total cost of ownership and increase reliability, and can also significantly reduce exposure and the risk of human error for electrical workers. To maintain safety and reliability, very strict codes and standards well above the basic NEC requirements apply. However, the foundation of our electrical codes and standards for healthcare environments was written in an earlier era when healthcare and energy landscapes were vastly different. The modernization of healthcare facilities includes a significant transition to electronic and advanced monitoring and control equipment.
So the difference between a hospital built today and 30 years ago is on many facets different. One, the technology that we're putting inside the hospitals. We have a lot more advanced technologies than we did 30 years ago. We have to provide power quality, much different than what we did 30 years ago. Reliability, much different. And the whole concept of a hospital, in my opinion, is changing across the country because some jurisdictions are trying to do more in smaller structures, more focused areas. So the structure's changing and the technology has changed considerably.
Although it seems like we have more frequent interruptions and downtime from utility companies, it's the use of these electronic loads that makes us more susceptible to short duration disturbances and power interruptions. Hospitals cannot withstand disruptions for critical life safety equipment and therefore require more significant considerations for protecting critical electrical loads. Additionally, cybersecurity considerations and electronic health record technology are critical to the operation of hospitals and for the benefit of the patients using these facilities.
So if you think about reliability in a healthcare environment, a lot of people will fall back and say, I don't want to die on a hospital operating room. Where in reality, the chances of that are very slim, right? For reasons of power reliability. But in essence, the real critical areas are those other areas you wouldn't think about. The emergency room, for not reasons of, I need to work on you, but I need to know your medical history. I need to know before I give you a medication that you are, you're not a diabetic, you're not allergic to penicillin, you're not allergic to certain things. And all of that information comes from communication systems that have to be up and running. So all of the aspects of codes and standards work to make sure that the doctor, the nurses, all have the equipment. I might need to get you to an MRI and take you up an elevator. If it's not working, what do I do? All of those things play together to increase safety from a reliability perspective.
Many other aspects of our healthcare system today require more power, more reliability, more efficiency, and more security. As a contractor, for example, you may not have the access to some of the equipment or controls that you need to fix a problem or upgrade a system. This added layer of protection also creates added layers of complexity.
A hospital's created a totally different work environment. There's just so much more involved at a hospital than there is a standard commercial building. So much more to be aware of, the procedures, protocols, and the coordination is all next level in a hospital.
Beyond the evolution of basic electrical system considerations, the role of rural and metro hospital systems has also changed considerably since the basic codes and standards were written. Although the codes and standards are the same, rural hospitals may be the only healthcare facility for miles, which necessitates the ability to operate under backup power for days or weeks at a time should a regional disaster occur.
There have been times in working in hospitals where they have lost power, and the generators for the life safety and essential power have kicked on. They have the redundancies built into their system to assure that they're not going to lose the life safety power that they need.
Healthcare facilities could include any of the following or more: hospitals, clinic or urgent care, doctor or dentist offices, surgery centers, imaging centers, university medical centers, nursing homes, medical or test labs, rehab centers, or medical office buildings, also known as MOBs. This series of videos will focus on hospitals as they include many of the other types of facilities, or at least address the considerations that you might worry about for one of those facilities. Electricians, maintenance personnel, facility managers, project managers, design engineers, and others are challenged with the nuances of designing, building, and maintaining these facilities. While this information can be relevant for any contractor in the healthcare construction space, the next generation of contractors will face even more difficult challenges, as they will not be able to lean on the mentors who have lived through the significant changes in this field.
One of the challenges that faces our industry, and specifically the healthcare industry, is the retirement of experienced designers and installers in healthcare. As those people retire, that expertise is lost and must be passed on to a new generation. The codes and standards are constantly evolving, constantly becoming more complex, and that requires a lot of dedicated effort, but it represents a real opportunity to differentiate yourself as a contractor or as a design engineer. So knowing these codes, knowing these requirements, getting experience on healthcare and installations is based on the growing market of healthcare that's going to continue for decades and decades to come. It's an excellent opportunity to differentiate and grow your business.
With so many codes and standards created around a hospital, how does a contractor even know where to start? Let's start by recognizing the unique part of a hospital's power system that makes a hospital different from typical commercial buildings. Being a contractor in the electrical industry, you're probably already aware of the National Fire Protection Association, or NFPA, as they write the National Electrical Code, or NEC. NFPA defines this unique part as the Essential Electrical System, or EES. The EES is a system comprised of alternate power sources and all connected distribution systems and ancillary equipment designed to ensure continuity of electrical power to designated areas and functions of a healthcare facility during disruption of normal power sources, and also to minimize disruption within the internal wiring system. This definition is critically important, but the NFPA 99 standard, where it originates, is just one of many relevant standards that apply to electrical components and systems within healthcare facilities.
So the scope of NFPA 99, to contrast it with the National Electric Code, is that 99 covers the performance, testing, and ongoing maintenance requirements for all the electrical infrastructure within the facility. The National Electric Code, on the other hand, would govern the installation requirements of getting things installed and making them ready for use. So for a contractor that deals with healthcare, you're really living in a little bit of both worlds. The performance requirements that you have to meet for the system that's getting installed, and the installation requirements to prepare that for it and make it ready for use in the facility.
It's not really necessary to memorize every code requirement, but it helps to have a good understanding of where we would look if we wanted to find the information. The codes and standards supporting essential electrical power systems in healthcare facilities continue to improve and evolve. NFPA codes form the fundamental standards for emergency power systems. The NFPA regularly publishes and updates several codes pertinent to essential electrical systems in healthcare facilities. This is a summary of some of the current standard code requirements healthcare facilities must comply with. NFPA 70, National Electrical Code. NFPA 99, Healthcare Facilities Code. NFPA 110, Standard for Emergency and Standby Power Systems. NFPA 101, Life Safety Code. NFPA establishes the requirements for essential electrical systems, while the Centers for Medicare and Medicaid Services, or CMS, adopts these rules for the inspection, testing, and maintenance of the essential electrical system equipment. Other organizations may be involved in the process by providing accreditation services. These organizations enforce the rules adopted by CMS. Most code requirements for emergency power are intended to assure that individuals inside can evacuate the building quickly and safely. Typically, this is required within a 90-minute to 2-hour window of time. Often, meeting the minimum building code requirements is not sufficient for maintaining healthcare operations or services when an outage occurs due to the nature of the occupants. Egress and evacuation is not always feasible for occupants of a healthcare facility. This brings up the concept of defend in place. Defend in place means you can't evacuate the people, but rather you have to accommodate the situation, oftentimes with excessive measures. Therefore, different criteria and requirements are needed for the healthcare electrical system during natural disasters, for example, where the normal source is unavailable. As a contractor in this type of environment, you would also have to consider how things would affect your role.
Defend in place in the hospital, you have to realize you can't move the patients out of the hospital. They have to stay. They are getting treatment for something that they need to be in hospital, so they cannot be moved. They need to have that care, so they have to stay.
Unlike in a commercial building, you cannot just simply evacuate every patient necessarily. They could be hooked up to life-saving devices.
When you think about the whole defend in place process, that whole concept, you have to have all of your systems analysis studies understood. You need to know what your fault currents are. You need to have done your arc flash calculations, done your coordination studies, and all of these different things that help reliability are based upon the one-line diagram. Even the electrical worker. If you're in a situation where you've got a hurricane and you have all of the patients in their beds and in their rooms and you're working to keep them living through whatever it is they're experiencing, and there is something going wrong in the hospital, you need to find that problem. The one-line diagram is your first place you're going to go to. And if it's from 1952 and it's never been updated, you've got another problem on your hands.
So let's look a little more in depth at each standard and see how it might relate to you as a contractor working in a healthcare facility. NFPA 70, also known as the National Electrical Code, or NEC, addresses primarily the installation requirements of electrical systems. It provides specific requirements for the installation of electrical conductors, equipment, raceways, signaling and communication conductors, and fiber optic cables. A portion of the NEC addresses maintenance of electrical distribution system equipment in accordance with the manufacturer's or industry standards.
Healthcare environments are all about reliability. And reliability is not something that you just install. You have to make sure that you maintain your power distribution system, just like you maintain your car or your vehicles. 70B, NFPA 70B, NFPA 99, maintenance is getting a much better focus these days. 70B is moving to a standard, to a U-Shell document. That's critical to improving safety and reliability in any power distribution system, especially the healthcare world.
It also provides guidance on specifying personnel protective equipment, or PPE, and electrical panel labeling.
So labeling, importance of labeling. The National Electrical Code recognizes the importance of labeling. We have specific requirements that you have to label the source of certain pieces of equipment and electrical distribution equipment. Why would we want to do that? We need to be able to identify, if I'm looking at a circuit, what is supplying it. We also are required to put a label on equipment to say what it is supplying. So the electrical worker who comes in after the fact, or the owner of the facility, is able to make decisions on what to turn on, what to turn off, and how to troubleshoot.
In addition to articles on installation requirements specific to healthcare, the NEC includes articles on emergency power systems and optional standby systems that may have applications in given areas of a healthcare medical campus. Some emergency system requirements apply to the life safety branch of the healthcare essential electrical system and are related to egress lighting, fire alarm, and standby power system support. These requirements take healthcare facilities above and beyond typical commercial buildings, and as a contractor, for example, this may include installing separate electrical branches, isolation transformers, insulated grounds, specific receptacles, earth leakage monitoring, and more.
So some of the unique aspects of a healthcare distribution system from a power standpoint is this requirement for a normal and then a backup alternate source. So the types of sources can be different, but they have to be independent of each other. So in other words, I don't want to depend on two separate utility sources to be my only source of power for a healthcare facility. One of those sources needs to be an on-site source with on-site capacity, storage capacity, so that it can run up to 96 hours without an external source, without refueling or anything. Because again, we're doing this defend in place type of architecture where the residents, the occupants cannot be quickly moved from the space. So that requires some different thought. From a source standpoint, we have to have redundant sources. Additional to that, we have to have redundant pathways to the critical loads.
The NFPA 70E defines special safety requirements related to arc flash hazards. The energy released during an arc flash can cause severe damage to equipment and, more importantly, injury or death to people working on or around the equipment. Arc flash considerations are especially important to contractors working in healthcare facilities because typically hospitals have large power systems and multiple sources that can make the arc flash incident energy levels very high. Beyond the safety aspect for personnel working on the equipment, the damage to the equipment caused by an arc flash could endanger patients, doctors, and other people working in the hospital if the power system is crippled. The arc flash energy that would arrive on bare skin or on the surfaces of any garments you are wearing is called incident energy and is expressed in calories per centimeter squared. The three main contributors to determining incident energy are time, or the duration of the arc exposure, power of the arc to the arc location, and distance of the worker to the arc. The time is dictated by the protective device clearing the fault. The power is related to the amount of fault current available from all sources of power. The distance refers to the arc flash boundary, which is the point at which the arc flash energy decreases below 1.2 calories per centimeter squared.
So when you think about electrical safety, there are basically three different type of hazards. You have your shock, arc flash, and arc blast. I always lump arc flash and arc blast into one topic. So you have shock and arc flash. Both of those are just as critical as the other. I mean, they'll both kill you. And as designers and as electrical contractors, we've got to be thinking about the individual who's going to be working on this equipment. We want to prevent them from accidentally coming in contact with something that's energized, which will help prevent shock and also help reduce the likelihood of having an arc flash event. For the electrical worker, it's life and death. And you have to regardless, even if you say you're going to establish an electrically safe work condition, you need to dress to be able to know whether or not you've established an electrically safe work condition. So arc flash incident energy is all about the electrical worker and going home safely.
Working inside this arc flash boundary requires that you are qualified and wearing proper PPE based on the arc flash label. As a contractor working on or around this equipment, you may find that arc flash labels are not available and you must determine how to approach the situation. This includes determining what type of PPE to wear and if you are even able to work on the equipment based on the risk associated with the level of the incident energy. For example, working on anything over 40 calories per centimeter squared is not allowed by the standards.
They call that a non-labeled environment, and that's why the tables exist. So you know, the IBEW and the electrical workers who are in front of that equipment fight for the what they call the table method. And at first, the engineer in me used to argue and say, well, no, you need to know the arcing current, you need to know the clearing time, you need to know all these details. And it hit home when Jim told me one day, he said, Tom, people are not dying because they're not wearing the right PPE. People are dying because they're not wearing any PPE. And a light bulb went off in my head because in reality, think about it, put yourself in that, you show up at a facility at 2 o'clock in the morning, the power down, or you show up at a hospital and the power's out, doctors are yelling at you and you say, I need to get this power up and running, I'm in a non-labeled environment, you're going to need to figure out what PPE you need to put on.
If I walk up to a piece of switchgear and it has an arc flash label on it, you always look for some type of a date as far as when that label was installed. At that point, you can talk to maintenance personnel and other hospital personnel about how many projects have been going on. If, for example, the sticker might be 3 years old, there could have been a number of projects that could have increased the yield of that arc. So it's always important to know how accurate that arc flash may actually be.
From our standpoint, we do look at the arc flash stickers if we have to throw a breaker or we have to turn a breaker on, so we know what calorie suit that we have to wear in order to perform that task. What I will say about arc flash studies, even though the industry is going to have in a direction to have that on every piece of equipment, things change so fast and construction gets updated and changed. Those arc flash stickers are not always the most updated.
This also means the responsibility to determine the levels of incident energy is on you or a qualified person. Most importantly, no matter what the arc flash label says, the calculated incident energy level assumes the equipment is properly maintained and tested for the protective devices to operate as expected. Understanding the label, knowing what PPE to wear, and the extra precautions in healthcare facilities makes Arc Flash a very important consideration for contractors in these facilities.
Yeah, I mean, Arc Flash has changed the way we do everything on a daily basis. Without 70E, a lot more people would be in more danger on a daily basis. It complicates things as far as getting the work done in a timely manner, but at the same time, I get to go home at the end of the day, where in some cases, people less fortunate have not gone home because those standards weren't in place.
Common misconception about the National Electrical Code and codes and standards in general is that there's some body of individuals who make these rules and inflict them on the electrical industry. When in reality, those rules are really created and made based upon feedback from individuals within the electrical industry, bringing their expertise, their experience, their awareness of this is a problem that needs to be addressed. Those committees sit together, create rules and regulations, and then they're delivered out to the electrical industry. The healthcare industry is changing every day. There are new solutions, new products being put in place that could present safety challenges that no one else would recognize outside of the electrical contractor who's doing that installation in a healthcare environment. When you recognize those issues, bring those to the table to the codes and standards world so that we can help improve the codes and standards that we use on a daily basis.
The scope of NFPA 99 is to establish criteria for levels of healthcare services or systems based on risk to the patients, staff, or visitors in healthcare facilities to minimize the hazards of fire, explosion, and electricity. When you think of NFPA 99, remember this is the Healthcare Facilities Code and it covers all the different systems in a hospital, not just electrical. For example, HVAC, plumbing, gas, security, and several others. As opposed to the NFPA 70 that addresses installation requirements, NFPA 99 addresses issues around system performance. Many of the requirements of NFPA 99 are often extracted and included in the NEC to make it easier for the user. With respect to the essential electrical system, NFPA 99 addresses critical facility power distribution requirements for a wide range of equipment, lighting, and receptacles specific to healthcare. It spans 3 branches within the essential electrical system and describes equipment for which standby power must be provided as follows. 1, the equipment branch, which is broken into equipment with automatic connections or automatic or manual connections. 2, the critical branch primarily includes task lighting, select receptacles, and select power circuits needed for effective facility operation. 3, the life safety branch is generally given the highest priority. It spans egress lighting, exit signs and exit directional signs, communication systems, generator set locations, elevator cab lighting, control and communications, electrically powered doors used for egress, and fire alarms and auxiliary functions of the fire alarm systems. Requirements of special note are those regarding generator backup for locations such as the operating rooms, critical care spaces, and medical labs. These requirements specify that after detecting a power outage has occurred, the generators must start and the transfer switches must transfer and restore power within a set number of seconds. In most cases, this is 10 seconds.
Some of the other unique requirements in healthcare after the facility is occupied is the requirement for ongoing testing of this essential electrical system. Each generator has to be tested monthly to at least 30% of its nameplate loading. Transfer switches have to be operated and verified that they will successfully transfer the load. And there's also other periodic tests of the generators at much greater loads that may require the addition of load banks, temporary load banks, in order to accomplish that periodic testing. But the ongoing testing and maintenance of these systems is something unique to healthcare. It's way above a normal occupancy type that requires, because of the critical nature of these systems and the areas that they're feeding where there could be critical patients. Many healthcare providers reach out to the local contractor community to help meet this monthly and ongoing maintenance and testing requirement.
When faults in the electrical system occur, the NFPA 99 standards for protective device coordination is a key element in ensuring that the system reacts appropriately to prevent a small issue from becoming a major outage.
Selective coordination is understanding how your overcurrent protective devices respond to a current that passes through them in that series circuit. You want to make sure that the downstream device opens, the upstream device doesn't.
NFPA 99 also provides guidelines regarding the operational aspects of the healthcare facility in regards to standby power. Lastly, NFPA 99 requires the use of automatic transfer switches, which by definition need to meet the industry standards for transfer switches, which would be UL 1008. Transfer switches are responsible for quickly and safely transitioning all electrical power consumed by the circuit, equipment, or systems connected to the transfer switch output between those normal and emergency power sources. The essential electrical system loads are connected to the load terminals of a transfer switch. In healthcare applications, bypass isolation transfer switches are often used because you can do maintenance on half of the transfer switch while still having a fully functional transfer switch to protect the loads.
Depending on the risk to the occupants of a given space, I might have to have a transfer switch that transfers between my normal and my emergency source through a transfer switch and then feeds into that occupant space. And then in that space, there's requirements for outlets that are fed from both a normal source and an alternate source or an emergency source. So those are typically red in healthcare. So you'll have normal outlets and you'll have red outlets in a given space, critical needs space, so that there are two independent pathways backed up by two independent sources to that particular patient location.
The NFPA 110 is the standard for emergency and standby power systems. While the NFPA was founded back in the early 1900s, the fundamental standard for the application and operation of emergency electrical systems, NFPA 110, was not formed until 1976. The NFPA continues to evolve and is reviewed and updated on a 3-year cycle. NFPA 110 defines the performance requirements for both emergency and standby power systems that provide an alternate source of electrical power to the healthcare facility. Think of generator design and installation when you hear NFPA 110. In the event that the normal electrical power source fails, transition to backup equipment must occur in a timely and reliable fashion. Systems addressed here include power sources, transfer equipment, controls, supervisory equipment, and accessory equipment needed to supply electrical power to the selected circuits. This code requires a routine maintenance and operational testing program after the standby power system has passed acceptance tests or after completion of repairs that impact the operational reliability of that system. It also requires a defined written schedule from routine maintenance and testing of the emergency power supply system, or EPSS. NFPA 110 presents installation, inspection, maintenance, operation, and testing requirements as they pertain to the performance of the EPSS up to the load terminals of the transfer switch. It requires that transfer switches be subjected to a maintenance and test program that includes all of the following: checking connections, inspection or testing for evidence of overheating and excessive contact erosion, removal of dust and dirt, and replacement of contacts when necessary. The financial support provided by the Hill-Burton Act in 1946 after World War II spurred the development of hospitals across the U.S. The first edition of the NFPA 110 standard for EPSS was published in 1985, which is about 35 years or so after many hospitals in the U.S. were built. The challenge in 1985 was applying the NFPA 110 requirements to existing systems. The NFPA 101 is the Life Safety Code. The Centers for Medicare and Medicaid Services, or CMS, currently require healthcare facilities to comply with the NFPA 101. This code includes requirements for standby power and emergency lighting systems in both new and existing facilities, specifies guidelines on such details as how long the generator should run and how much fuel must be stored on site, weekly operational inspection and testing of emergency or standby power supply systems and components along with monthly load testing. Testing documentation must be maintained. Nearly all facilities participate in Medicare or Medicaid programs except government facilities such as VA and DoD as one of the primary insurance reimbursement programs for over 75 million Americans. To participate in these programs and receive reimbursement, a hospital has to comply with the conditions of participation. These conditions adopt NFPA 99 Healthcare Facilities Code and NFPA 101 Life Safety Code. Through those adoptions, compliance with other documents such as NFPA 70 and 110 are required to be followed as they are referenced in NFPA 99 and 101. In some situations, CMS deems their authority to inspection and enforcement to accrediting organizations such as the Joint Commission. The Joint Commission is a global driver of quality improvement and patient safety in healthcare. Some people that have been in the industry for a long time may still refer to this group as JCO. Through leading practices, unmatched knowledge and expertise, and rigorous standards, the mission of the Joint Commission is to continuously improve healthcare for the public. In collaboration with other stakeholders, they do this by evaluating healthcare organizations and inspiring them to excel in providing safe and effective care of the highest quality and value. Contractors need to understand the Joint Commission standards because they directly relate to the requirements adopted by CMS and can be traced back to the NFPA codes mentioned earlier. Two key aspects of the Joint Commission standards are for reliable emergency power sources, as well as testing, maintenance, and documentation requirements of the emergency power systems. These requirements are the basics to meet Joint Commission accreditation. Joint Commission EC 020503 requires an inventory of pieces of equipment or components. Joint Commission EC 020507 lists elements of performance including testing and related documentation. This Joint Commission standard relates to the inspection, testing, and maintenance requirements of emergency power systems. However, it does not require that the organizations have to have the various types of emergency power systems identified in the code. The intention of this standard is to provide guidance for testing of emergency power systems so that these systems are less likely to fail during a power disruption. Testing these systems for enough time and regularly helps to increase the probability of identifying reliability issues and reduces the risk of losing emergency power when it is needed. Beyond understanding the codes and standards that apply to healthcare facilities, contractors need to understand how a hospital's electrical system is generally defined. This includes a detailed understanding of the essential electrical system, emergency power supply system, and the emergency power supply, and how they interact with the utility source and the critical loads in a hospital. The second video in this series highlights the essential electrical system in hospitals. Contractors also need to have a deep understanding of what makes a hospital different when building teams to plan or complete work, especially when it involves the electrical power system. The concept of defend in place is crucial to the well-being of individuals in a hospital because most of them are not able to evacuate if something unexpected would happen and power was lost. Video 3 in this series discusses the proper planning and procedures to help keep minimum disruption to patients and other personnel within a hospital and keep everyone, including you, safe. Safety is especially important when working in a hospital. Between the complex electrical systems where shock and arc flash are a serious concern, you also have to be aware of the patients in the hospital and think about things like infection control, for example. A contractor should feel comfortable being able to read an arc flash label and understand the dangers that are associated with the equipment where it is located. They should also know what PPE to wear to protect themselves, especially given that energized work is often required in a hospital. The fourth video in this series discusses electrical safety and healthcare applications. Contractors have a special role in working in healthcare facilities because of the inherent risk and danger associated with electrical power systems. To understand how you should approach working in these facilities, you should make sure that you understand the relevant codes and standards and how they apply to you. In addition, you should understand how power systems in hospitals differ from typical commercial buildings and how you can build a team around you to make sure you complete projects safely. To learn more about electrical power systems in healthcare facilities, contact us or your local Eaton representative to schedule a visit to the Power Systems Experience Center today.